I have? I put a lot of stuff on D2L. Put a lot of stuff on D2L. So under, this is our D2L homepage under test review and solutions. I have test number 2, but I just passed out a hard copy. But I've also created a solutions for you. Just in case I run a little short on the lecture, you at least have the solutions available to you. Just a note, I did have to reword the very last problem. So I'll make sure I get to that problem. It's only a slight reword. Okay.
Is there a number 8, maybe it's an answer, I'm not sure.
Possibly.
Okay.
I make mistakes all the time. So, okay, we'll get to it.
Yeah.
Thanks. Yeah. What else I've been doing? As people have been asking me homework problems, I've been putting them up here. So I've got like 4 problems, or 3, worked out from chapter 18 on sample distributions. And then I put up a chapter 19, which is the confidence interval. I picked one that's going to be just a lot like the test. So this is a good homework problem to look at. Okay. So we'll do a 10-minute on confidence interval, then we'll get right into the practice test. Okay, so these were homework problems. These are the ones on D2L, worked out. So chapter 18, number 6, and number 7. Okay. Okay, so I introduced a confidence interval in chapter 19. It very much mirrors the sampling models we've been building. Okay, and what I want you to think of when you think of a sampling confidence interval is think like an election, a pollster. I'm going to collect a small sample, let's say 1,000 people, and I'm going to ask them who they're voting for. I want to take that number and come up with, hey, what do I think the entire population is doing? That's what a confidence interval does. Okay, and so we went through this sample. This was a sample of, remember the diseased sea fans in the ocean. Okay, so this is the scientific method, by the way. Okay, so a scientist sampled 104 sea fans or coral. It's a sea fan, a certain type of coral, in random locations. And then he was testing them, all 104, and he found that 54 of them had this disease in it. Okay. Well, if success is that they have a disease, the proportion is 51.9 of that one sample. Okay. We'd like to take this information and make a claim, hey, what are all sea fans? What do we think the proportion is for the sea fan? Okay. So I went through all the math describing a confidence interval for you. But what I'd like to do is rework it as if you're working this problem on the test. Okay, and so the real question is, when you're calculating a confidence interval, is our sample suggests the proportion of infected sea fans is 51.9%. The question is, what's the real proportion? Okay, in other words, what's the population proportion? Okay, and so how do we work this? Well, like you work this, we have enough information here. I've lost copies of, does anybody have an extra, maybe? Yeah, thank you. Sorry, I didn't realize I didn't make enough copies. So this is a sample. We can generate a model of what the sample proportion should look like. Success? This is, yes, number of success. So this proportion estimate is the 54 over 104. Does that make sense? Yeah. Okay. Okay. We expect if I did another sample of 104, the proportion is going to be slightly different, right? It's not good. Okay. So this is a random variable. Okay. We have to build, the estimate or the mean and standard deviation of this model. Okay. But if you notice, with confidence interval, you no longer have the population proportion to work with. Okay, so we use the sampling proportion as a surrogate. Okay, so we're going to center it around the 5.19. We're going to calculate our standard error. So we've switched the name. It's not standard deviation, it's standard error. Standard error is when you use your sample number. It's strictly a surrogate. We're going to treat it like a standard deviation. Okay? And so this, if you remember the formula, I will have these formulas for you on the test. 104, if you calculate, you get 0.049. Okay. Is this looking familiar? This is actually chapter 17, part of this. Okay. So I can, this is a sampling model is a normal model, right? Everybody remember that from chapter 17. Okay. So I can draw the mean and do the 1 sigma, 2 sigma, 3 sigma. Okay, so let's do that. 0.159 or 519. Okay, if I add 1 sigma, I can draw these anyway. 0.568, 0.617. Hopefully you guys are helping me add. I can't. Anyway, 447. Thank you. 470.421. Thank you. Okay. Does everybody understand at least what we just did? Okay, the mean, the 1 sigma, the 2 sigma. Let's convert these to percents. They're easier to look at. This middle one is 51.9%. That's the average of what we think the population proportion is. If I go up 1 sigma, let me go up 2 sigma, 61.7%. Down 2 sigma, 42.1%. Okay. Do you remember what's the chance that I'm between the two sigma boundaries? Say that again.
1 minus the other.
Not really. Between the 2 sigma and minus 2 sigma? 95%. Okay. So if we choose to use the 2 sigma boundary, we just generated a 95% confidence interval. Okay. So the book uses a Z star for 2. That's just how many sigma away am I. That's all it is. If we're using a value of 2, this confidence interval is a 95% confidence interval, and it is, okay, we think, we say, it is, we say it in words, we are 95% confident the true row, okay, this is our population number, is somewhere between, and then 42.1% and 61.7%. Okay, that's really it. I mean, that's literally generating your sample model. Do the 2 sigma if I'm asking for 95% confidence, and that's your boundary. Okay, so I'm not sure exactly what the true proportion is, but I'm 95% confident it's between these 2 numbers. Okay. Its average is still 51.9. Okay. Is this making sense? Because this is kind of the type of problem I'm going to put on for this. Very standard. You get a set of sample data. You get no population proportion value. You're going to use this, generate your sampling model, do the 2 sigma boundary, and that's your 95% confidence.
How would the question be worded?
It would be like this. Like this. Our sample suggests the proportion of infected C fans is 51.9%. What's the real proportion? And then it would probably be like generate the 95th percent confidence for the real proportion.
Okay, so then we just do we just take the percentage that we have, and we know that that's going to be our rho, our p hat, right?
Yes. Yep.
Okay.
Yep, yeah, this is our one sample. Okay. And that's used to generate your boundary. Yep.
The 0.481 is N. The
This guy?
Q. No, the 0.481.
Yep, it's always
Okay.
1 minus.
Got
Yep, yep, that's Q. Okay.
And the n is what?
My sample size. Yep. So if I don't like, so this is a good comment, or a good observation. If we don't like this boundary, this is actually pretty wide. It's like there's a lot of, proportions, there's a lot of space in here is what I'm saying. If I don't like that, I'd like to tighten it up. I just increase n. And 104 isn't enough. Take more samples. Use that estimate from the more samples. This value shrinks because n is increasing. My model tightens up, and I get a narrower boundary. Okay. Okay. So that's all I want to do. The last problem. I'm going to keep it very simple. Okay. All right. So let's go over the test. Okay. I do want to make sure I work the last problem because it's going to be another confidence interval question. But let's start at the beginning because you haven't seen the beginning stuff in a while. So read that first problem. Okay, so we're talking problem 1, 5 multiple choice questions. You're taking a test. There's 4 answers that you're choosing from for each of the 5 questions. There's an A, B, C, and D, essentially is what it's saying. Okay, what else do they say? They've got a couple, what's the probability you get none of the questions correct? Okay, an assumption here. You're assuming you're guessing. So you are randomly guessing the answer. Okay. Anybody? So I got 5 questions. Each of them has 4 choices, and you're randomly guessing. Okay. Anybody know how I would set up the probability you get none of them right?
Is the complement all?
Complement would be, well, 1 minus. It's not all. Could you, actually a good thing, don't jump to complement right away. Is there a way you could write this by saying, well, to get none of them, I know what I get on the first, I know what I get on the second?
I mean, my vocab is probably going to be off here, but just wouldn't it be 0.75 to the fourth or to the fifth?
Yes, but I'd like a little more detail. So how would you write this out?
Isn't it just a normal?
It is definitely not a normal. You could, and the reason why is because you've got I got it right or I got it wrong.
Okay.
So it's not a normal. Yes, you
So
could do
would it
this
be
as a
geometric?
binomial, but you don't have to. Okay, Andrew, you got it?
You get the probability that none are correct. So probability that first is incorrect, and second is incorrect, and third and fourth.
Does this make sense to everybody? You are correct, by the way. So there's 5. What's the probability of getting one wrong if you're guessing? That's where the 0.75 comes in. So 0.75 to the 5th. I got 23.7% for that. Does that make sense? How you set it up? Okay. B is close. Get all of them right.
So would you do the same thing?
What
Yeah,
did you, how did
but
you, what, the 0.75, wait, where did you get that?
Well, there's 4
Right.
possible answers.
Uh-huh,
Only one of them can be right.
right,
So 3 out of 4 are wrong. If
right,
you're randomly guessing, 3 out of 4 is 75%.
okay.
That's where, yes.
Do we have to write it like that? Do we have to, or is
Like-
it around like a key?
No, if you do that, so the caution, better get it right. If you don't get it right, no partial credit. If you go through here and you're kind of telling me what you're thinking and you make like a math error, I can unwind it and say, oh, that was just a math error versus you don't know what you're doing.
Okay.
So you don't give me any details and you get it wrong, I have no justification for it. So, okay, so is everybody good? First is correct. Second, correct. All the way up to 5th, correct. Is this making sense? Okay, so probability of getting something correct is 0.25. 0.25 to the 5th,
0.0009.
almost nothing, yeah. I got 0.1% with rounding. So almost not gonna happen, pretty much. Okay, with guessing. Okay. Yeah, exactly. Possibility and probability, yeah. Okay. How about C? Get at least one of the questions wrong. That's where you're gonna take. Yes, thank you. The at least one especially. So there's a lot of different ways you could get at least one wrong. So think of this as the complement. 1 minus, what's the opposite of at least one wrong?
3 right? Or at least 4 right? 'cause there's
None wrong. So at least one wrong, so that's 1 wrong, or 2, or 3, or 4, or 5. This is 1 minus 0 wrong, or all correct. It's the same, depends how you think of it. So 0 wrong, that is all correct. Okay, which you've already calculated the all correct. So this is 1 minus the 0.1%. Or 99.1%. 99.9, sorry. Okay. Is this making sense?
Yes.
Okay.
No.
How about number 2? Oops.
Quick question, is there any way that you can post exactly what formulas you're gonna be giving us, just so we can have an idea?
Yes, I am. I'm just not done with it. I'm sorry. Yeah. I don't know what I did with my. Great. Where did it go? Did I delete it? Let me save it. Something's going on. Okay. So I'm gonna add. Okay. Good. All right. So number 2.
This is that circle thing, right?
Yay, thank you, Venn diagram. So, and then another thing for partial credit. It's up to you, you don't have to do this, but this helps. So we're gonna say T is they're having turkey, H is they're having ham. They gave us probabilities. If you're seeing a Venn diagram, I think that's a good thing. Can you help me fill this in?
0.16.
Okay, yep.
And turkey's 0.12.
Okay, so yeah, so we said probability of turkey is 0.58. That means the two of them are 0.58, so 0.42 is there. Probability of ham was 4.4. That means this, thank you, 2.8, yep. Add those together,
0.14 is left.
0.14, thank you. Okay. Make sure they add up to 1. Okay. And then we can answer the questions. So in this one, so seriously, and not to make fun of you guys to answer this, you do all the work here, and then like the A, B, C, D, I'd expect just percentages. And I'm good with that, because I'm going to look and see whether you built the Venn diagram properly. Okay, so if you do A, Nobody, so they have neither turkey nor ham.
0.14.
Yep. So I'm very much expecting just numbers here because you did the Venn diagram. So
There's a percentage as well, is that considered right?
either one. Yep. Oh yeah. Either one's good. Percentages is probably what I prefer. I'll take decimal. Okay. What's the probability that they have only ham without having turkey?
0.28.
Only ham without turkey.
0.28.
No. 0.28.
That's what I say to you.
I'm here at 5.8 back
No,
there.
leave it on the side.
Oh, got it, okay. All right. What's the probability that a randomly selected family having turkey had ham?
0.6. 0.16.
Well, it's not.
Actually, 0.16 divided by.
Thank you. Okay, so here's where details would help. You have to recognize C as a conditional. We're asking the probability that they had ham. We know they had turkey, so that's given they had turkey. Okay, it's hard. I don't like that sentence. I'll make sure the sentence is worded a little clearer. Okay, that it's something this given. Okay, and then I think I heard Andrew say this is this. So this will be on the formula sheet, the conditional. Okay, and then both of those are from the Venn diagram. So everybody agreed 0.16. Here's the one people sometimes mess up. Probability of turkey, both bubbles. So 0.58. If you do that, I get
276.
Yeah, 276. Okay, question. The events turkey and ham, that's why I made the T and the H. Are they disjoint?
No.
No. Why? Yep. I'd accept a couple things. Oh, I'd accept just saying there's overlap. I'd accept you saying that means the intersect is not 0 because it's 0.16. So this is the definition of disjoint. Their intersection is 0, and it's clearly not. Okay.
When you say they overlap, that's still cool enough?
Yeah, overlap's fine. Okay, number 3.
Just, I know this is, but disjoint is just like they're not together, right? Disjoint, separated, right?
Yep. We're going to work an independent on problem 4. Okay. Suggestion, and I've been doing this. I've asked you what kind of model is it. I'm trying to make you think. What kind of formula should I use? So can you read through this and tell me what kind of model? We got normal, we've got binomial, we've got geometric, and then you have sampling models. Yep. Okay. A suggestion. If it's a sampling model, I'm trying to help you a little bit. I will literally say sampling in the problem so that you know it's a sampling problem because I've just kind of thrown it at you. Okay, so this is, so it's binomial. So do we know success and failure and P and Q and N? What are they? Automatically know Q. Okay, did we know N?
Why is it binomial?
Binomial because,
They can have a computer, they can not have a computer.
well, that makes it Bernoulli. So it's a good question because success, failure, you've narrowed it down to 2. It's binomial or geometric. Okay, so then you got to ask, okay, if they're asking for the first time you get a success, it's geometric. This isn't first time. they're saying out of 3, they're asking what's the probability that a household owns at least one owns. So that's, you could be 1 out of 3, 2 out of 3, or 3 out of 3. That's binomial. Does that make sense?
Geometric will be just one success.
It'll say, give me the probability that the first family that owns a computer is like the 3rd one chosen. That's geometric. Okay. Good question. Okay, so we want a probability, right? Oh, by the way, what was n? I'm sorry.
3.
3. Okay, so do we want expected value, or standard deviation, or probability? Okay, all 3 are going to be on your sheet. Just make sure you answer what they're telling you. So, random variable x is number of families with computer. It's a binomial. Okay, so we are saying x at least 1. 2 ways to do this. How do you want to do it?
Do the 1, 4, 2, or 3.
Yep, so that's one way. I usually do this where it's not obnoxious. Okay, yeah, that's 3 terms. There's another way to do it, which is what?
Combination.
No, 1 minus x equals 0. Okay. So easier way, not impossible way. I mean, you can do either one. Okay. So what will be on your sheet is these equals, how to get those. Okay, so this is combination, your sample size, the number of successes. So p 0.565 to the first, because I only have 1, 0.435, all the rest are failures. Plus combination 3, here I have 2 successes, so 0.565 squared, 435 to the first, and then finally all of them successful. That means no failures. Okay, and when I did this, I got 0.918. Okay. This way, you're gonna get the same answer. 1 minus, okay, 0 successes, that means combination. Out of the 3 families, 0 are successful. 5, 6, 5, none of them were successful, all of them did not. Okay, and this is also 0.918 when you get that. Okay. Let's do this one on the calculator, just because it's fewer terms, just to practice. Okay, so just a suggestion. So 1 minus, I'm going to put those combination and those 3 factors in a bracket.
What if your calculator doesn't do that, but it does the X exclamation point? How do you do that?
Can I show you after class? Okay, I'll show you how to do that.
Okay.
And I will have calculators here if you want to.
Okay.
Okay, so I'm going to put that combination, this in a bracket on the calculator. If I was doing this, each one of these would be in a bracket. Okay. So bracket combination. If you remember though, you've got to do the 3 first. So got to hit the 3. That's your n. To get the combination, you're going under math and paging over to probability. You're coming down here to combination. It's just pasting the name on it. Okay, in that particular case, we were doing 0. And then, I'm sorry, this is what I put in the bracket. And then times, okay, so it was 0.565. In this case, 0 of them were successful. And then times the cube, 0.435 to the third, and then hit enter. And 0.91, yeah, 0.918. Okay. I know that was fast. Everybody good?
I'm recording this, you guys, and I will upload it to YouTube if you guys want to go over, so that will be on there. So, just so, I mean, seriously.
No. Okay. Okay, number 4. I don't want to do the table. Well, maybe I have to. No, I don't. So this is a contingency table, excuse me. We got 2 variables. If you want, you could convert this to a Venn diagram. Okay, so it just depends on what you're okay with dealing with. Okay, so the question, probability, a student is female. So I'm starting simple and then I'm getting into other more difficult questions. How do you get probability of female? Everybody good with that? These first couple questions are going to actually look like chapter 3 questions, but we did kind of do them again. B, what's the probability of the student ate breakfast? 191, 331, so 0.577 or 57.7%. Okay. What's the probability that a randomly selected student is a female who ate breakfast?
199 over 1. Natural.
Female and breakfast. Okay, so 125, is that what you said, 125?
Yeah.
125 over 331.378. Okay, here's wording I prefer. So if you remember my comment on problem 2, this is clear wording. What's the probability that a randomly selected student is female given the student ate breakfast? Is everybody good? It would be female given they ate breakfast. Okay, I need to write this out. F and B all over the B. Okay, we've calculated all of them above. Okay, so 378.577, 0.655, 65.5%. Okay, again, the conditional formula will be on the cheat sheet. Problem E, the reverse conditioning. What's the probability that a student they ate breakfast given that they're female? It's just the reverse. Okay, kind of follows the same pattern. B and F.
So,
Yeah, that's fine.
what is the 3.78 over 0.575?
Which one are you talking about?
378, the bottom one.
Yep. Because we're talking probabilities now. I think you need to realize it's a conditional, and that this is the definition of conditional. You do the intersection of those two in the numerator. The condition is the probability, that's your denominator. And since we already have probabilities, just use those. You don't have to use the numbers. Okay. Okay, so this would be, it'd be nice if you knew F and B is the same as B and F. Okay, so same 378. My denominator given is the 577. And so, oops.
So would it be 0.60?
Yeah. 601, and that is 0.629. Bless you.
Thank you.
Okay. Question. There's 2 random variables, breakfast and gender. It'd be breakfast, yeah, and gender. Are they independent? Do you remember how to test for that?
Greater than 5%?
What graded, we'll have a discussion about that. How do you calculate it first? What does independent mean?
Well, we know that one is 20. The female in breakfast score is grade 7, but we have to calculate the other parts to see if it matches up.
Okay, so what you're saying, breakfast and F is equal to test. Does it equal that? Because if that's true, then you say they're independent. Okay, so like you said, we know this is 378, breakfast, 0.577, female, 0.601, and okay, this is what I got. Okay, we had a 5% rule before, okay, but then I made a comment I'm really kind of looking for a lot closer than that. So this is close enough, you know, either say yes, these are close enough, or say no, they're not close enough, okay. If you want me to pick a number, let's pick 2%. If it's within 2%, say they're independent. If they're not, so new rule. I'm just pulling it out of my head. So new 2% rule. This is the thing about probability. Just state your assumptions and you're claiming it. Yes, Dan.
Oh, sorry. What are you comparing right there?
I'm comparing the intersection with the multiplication of the individual probabilities. If they're independent, they're equal, and we're saying equals within 2% now.
Alright, but if you're finding probability of B and F, isn't it the same thing? Aren't you just multiplying the two?
No, because it was given to us. It's we calculated it, the 125 over 331. So.
Okay.
This is only true if they're independent, and that's why we're using it as an independence test.
So if they're within the 2%, then they are
Independent. Yeah.
But if they're not,
If
then
they're far enough apart, they're dependent. They're not independent.
So they're dependent.
Yes. Yeah. This, it's not 2%, so they're dependent.
Next test is gonna be a warm symbol.
Yeah, absolutely. I keep changing it.
You can use the males too, but we had the figures.
Yes, you can. Yep. Yes, you could do. You could do not breakfast in male, and Yep. Okay. All right. 5. Everybody's favorite problem. What does 5 look like? A tree step. Yep. So it's a Bayesian. It's happened both classes today, halfway through. Say it again.
Have you ever intentionally hit not on the dot and see what it did?
No, well that's probably what I do to knock it out of calibration. My handwriting's bad enough. Okay, so anyway, if you have a problem where you're being given conditional probabilities, okay, chances are it's going to involve Bayes' rule. Okay, so Bayes' rule is this: A given B. This will be on your sheet. So that's Bayes' rule as we've been talking about it. Or I could expand the denominator. Okay. I will explain the denominator to you. You can actually see these out of the tree based on what was said. Okay, so does anybody remember building the tree? Yeah, why smokers first? Because it's the issue is someone's a smoker and then they have a lung and it's do they smoke or not? Do they have a lung condition or not?
He's a smoker. Does the 25%.
Yeah. Whatever variable they give you the individual probabilities, you want that to be your first decision. Okay. So the first decision is, hey, does the person smoke or not? Okay, because we have those probabilities. So smoke, smoke not. Okay, 0.23 smoke, that means, these have to be 100%, because you either smoke or you don't. Okay, the next decision is, do they have the lung condition or not? Both of them branch off lung or lung not. Okay, so these were the conditional probabilities given. This probably said the probability of smokers who have the lung condition is 0.57. That's a conditional. Okay, so that means 4.3 doesn't of the smokers. And then I think they said 13% of non-smokers have the lung condition. That means 0.87 don't. Okay. Is everybody good with the tree? At least building it. Okay. Yes, Stan.
To get the 13, or the 13%.
Yep.
We just do, that's good. So then, alright.
57.
Okay.
Gotcha.
So all these branches, I think it's good to write them out. If I go up the branch, this is probability of S and L, intersected with L. That next branch, smokers and not lung. And then getting the probabilities, I just multiply the two numbers together. Yes.
What is your 5C at the bottom underneath?
At smokers.
Oh,
complement.
Okay.
So just my bad handwriting. Not smoker and lung condition. This bottom one is not smoker and not lung condition. Okay. And this should be all the probabilities you need. Okay. So I have all the information here. If I'm being asked a conditional probability question, we happen to be asked that. What is the probability that someone who has lung condition was a smoker? Okay, I'm going to reword this. I'd say, what's the probability of that someone has a lung condition? No, someone was a smoker given they have the lung condition. That's what we're calculating. Okay, this will be on the sheet. So what you need to calculate is, it's not letting me move it. Let's try this. Sorry guys, the computer's really messed up today. S and L, and then let me write it as probability of L. Okay, and then you should be able to find them in the tree. Does everybody see the numerator is that top branch? Okay, it's going to be the 0.23 times the 0.57. Divided by probability of L. Okay, this is a single variable again. Okay, so what you have to do here is look at the four paths and how many of them have L in it. Not L complement, but L. That one does and that one does. So you have to add them together. Okay, so this is 0.23 times 0.57 plus that one 0.77 times 0.13. Okay. And if you do that, you will get 0.567. So someone who has the lung condition, 56.7% that they smoked. Okay, questions? It's a lot. I know I'm throwing this at you really quick.
Yeah.
This is a very short summary of a long lecture, so. Okay, look, I need to move on, so let me, if you need to stay after, we can talk. Okay. Number 6. What kind of words can you pull out of number 6? Say it again. The mean, yeah. What else? It's a sampling distribution. Okay. So when you see this, I really hope you're good with, just humor me and do the bubbles. Okay, is this a sampling model of proportion or mean? Proportion, right. So that means my population parameter is a proportion. I have a sample size. I probably have a sample, maybe I don't, that they collected. Okay.
And what's it that told you that this is like a proportion again?
Because of the 14%
Okay.
probably. Okay. Do we have N?
14.
128. What's that 14%? Is it population or is it a sample?
Population.
Population, yeah, because they think that's in general. Okay. That's important to distinguish those two. Okay. So that's all they've given us. They want us to describe the sampling model by naming it and telling us the mean and the standard deviation. So what's the name of this? Sampling distribution for proportion. You only got two options, for proportion or for mean.
Yeah, I'm having a really hard time figuring out when to do the proportion or when to do this. That's simple.
This-
You know what I mean?
The what?
But I'm having a hard time figuring out when to either do SD of Q or SD of Y.
So you got to look at the data they've given you. Is it something that could be broken down into a success failure? That's a proportion problem. Or if it's like, a quantitative value. Like I think the next one is it snake length? No, test score. It's not success or failure. Someone got a 50 on a test or they got a 20 or that's a quantitative. It's going to be something I'm going to take a mean value of.
I guess I'll just ask you.
Okay. All right. So, anybody remember what the mean and standard deviation of this proportion model is?
Standard deviation would be square root of EQ over N.
Okay. It's a standard deviation because I'm using the population. So let me do the formula. P times Q over N. This is 0.14, 0.86. N is 128. You get 0.031 if you round it. Okay, that's standard deviation. Do you know what the mean is? Anybody? What should it be centered around? Yeah. $1.14. Okay. So how do you draw the model? What is it going to look like?
Oh, is N, wait, what is it? What is at the bottom of the P and E? What is that?
N,
Okay.
sample size. What kind of picture are we going to draw for the model? No model. What are you going to label it with? Say it again. Yeah, what else? A couple of them. If you want to do all three, great. But if at least do two, and I know what you're talking about. One more. I can't think.
Now you're like us.
I know. Anyways, that may be wrong. I'm just losing track of it. Okay. That's a labeled sampling distribution model. If you really want to be repeat that there. Okay. Sketch, clearly label it. So these were the mean and standard deviation. This is the sketch it. This is A. This is B. Okay. C is always going to be, you're going to use the model. It's why I'm forcing you to draw the picture. Okay. So what is the probability that in this group over 18% of the new cars will be found to have electrical problems? How do I label over 18%? on that picture. Say it again.
P-score?
The question was, how do you label it? I know how you find it. Yeah. I'm going to be looking for this. So 0.18 is about there. That's what I'm looking for.
Okay, and this is one of those things where it doesn't have to be exact. Like I don't have to bang myself. I just have to get a look guesstimation. Okay.
Yep. Okay. How do you calculate that percentage? Z-score. Okay, so you could do Z equals 0.18 minus 0.14 over the standard deviation. You're going to get a Z value. You're going to look it up. Okay. Aren't you going to subtract it from 1, the value you look up? Z table gives you this. Hold on, Denise.
Okay.
Okay, and that'll give you that percentage. Okay. Denise wants to do normal CDF.
Well, I wanted to know. I want you to write down the answer to that, so when I'm looking at it, I'm not like, what? So I'm just. I'll tell you.
CDF. Anybody remember how to use the normal CDF option on your calculator? It's lower bounds, upper bounds, mean, and standard deviation. Okay, usually you grab these right off the table, or the graph, sorry. So this is normal CDF. I'll plug this in, by the way. My lower bound is the 0.18. Okay, if you remember the upper bound, since you're going all the way up, just pick some really ridiculously large, like maybe 2, or it's a proportion, so 100%, 1. Do the mean, 0.14. The standard deviation, 0.031. Okay, let's do that. Okay, so let's clear this. It's under distribution, so it's above the bars button. So second bars. If you go just down one, that's normal CDF. Okay, it wants you to paste it in there. So the lower bound, 0.18. The comma is just above the 7. Okay. Upper bound 1.0, mean 0.14, standard deviation, what was it?
0.031.
0.031, thank you. Hit enter. 9.8%.
Can we just use
Looks reasonable. Say that again, I'm sorry?
Good. This is like on the calculator how to find like use a Z table within the calculator.
Just use this to get your Z value, look it up. You'll be subtracting it from 1, because the Z table will give you this percentage. You'll subtract it to 1 to get that to match. You have this, I do, yeah. You get to do whatever you want, a Z table or the calculator. Yes, Andrew?
As far as the standard deviation, you put 0.01. On the example or the solution center you have, you went to 4 decimals and it changed the overall CDF to 9.6. And as long as we show our work that we did.
Yeah. I'm not going to look for exact. I'm going to look for it. I'd count it wrong if you gave me 50%. You know what I mean? So, yeah, but I'll look at your work. Okay, yes.
How many decimal places do you
Give me one beyond, give me a tenth of a percent. Okay. How is 7 different? You're going to have one of each. Yep. So what's going to be the name? Sample distribution for mean. Okay. Bubbles, they look different. How do they look different when you're talking to mean? I still have an N. That's the same.
Y bar.
Yep, that's my sample value. What do I have over there? Population, do you remember?
Mean and standard deviation.
Yep. I call it mu and sigma. Okay. Okay, so why is this for mean? Because we're talking a test score, and actually in the problem they give us a mean and standard deviation. So
that's like a little Y dash, right? That's what
yes, it is. Yeah, Y bar. That's like a sample mean.
Okay.
Okay. Okay, so they gave us a lot of numbers. What do I do with 21.4? Where's that? Which one?
Population.
Yep. Where's the standard deviation? Okay, what's my sample size? 25. What's my Y bar? Yeah, but, yeah, we'll talk about it in a second. You could leave that blank. Hey, they're really not talking about a single sample, okay? But I'm okay putting that there. All right, we have enough. We could generate a model of the means, right? What should they look like? Anybody? Do you know what the expected value of the sample mean should be? Yep. It's mu. This will be on your sheet. Okay. That means there's also a standard deviation. Do you remember what that was?
It's the SDP over the square root of n.
Yep. Standard deviation over square root of n.
That's what I was talking about a second ago, and I'm not sure when to use SDP or that.
Got it. You use SD whenever you're using population parameters. You use SE only in confidence interval at this point, but you're using sample data. Was that your question?
Yeah, just I'll ask you in class, but it was not SD, but SD or P. You know, the portion versus.
Got it. Think of it, test scores. It's a score. It's not a true or false or a success or failure sort of problem. So everybody's, I've got a bunch. Someone got a 25. Someone got a 15. It's a quantitative variable. So it's a mean. Okay. Okay. So how do I draw the model? Yep. Centered around. Say it again. Yeah. Do a couple sigma. Okay.
What is that sound?
Say it again.
What is that sound?
Oh, I have no idea. Yeah.
Doing a video next.
Yeah. So the question is in the probability question is what's the probability that the average composite score, so they're looking at 25 students. The question is what's the probability that the average score is 22 or above? Can I use this?
You have to go out more.
Say it again.
You have to go out another sigma.
Probably, yeah. This is a model of mean. They're asking me a question about mean. Is the mean 22 or above? So yeah, you're right, I need to go out of another, but it's gonna be somewhere up there. Actually,
It would be on the.
you're right. So this is an interesting one.
So another thing, can you do the normal model since it's the success fail condition?
Say that again, Justin, I don't follow you.
Can you still do the normal model since the success fail condition is not that?
Success fail.
100% on 25, it's less than 10.
You're right, we didn't check those. N times. Yes, you can, but you're not supposed to. So I'm not going to have you check. Good comment. I had in passing in this chapter talked about the N times P, N times Q. Okay, we're going to deal with those a lot more. The rest of 1920 and beyond. So I was not really doing it here. So let's don't check those conditions for this test. You'll be checking them next test. Okay, but thanks. Good comment. Anybody know how I can get that probability?
C-score.
Yeah, but you noticed something.
It's the same as the 3 sigma, so.
Yeah, I'd be okay if it's really close to a boundary or like on the boundary. I'd be okay with you using the known percentages. So this is 99.7. So that means 0.3 on both sides. So 0.3 0.15%. So if it's on the boundary, go in and do that versus if you want to save some time. Okay.
Let me go on and tell you how I would do the normal CDF function in this. Lower bound, 22. Upper bound, I'm just picking a really large number. I don't know, 50. Mean of 21.4. Sigma of 0.21. If someone wants to plug that in, I bet it's close to 0.15. Okay, questions? Yeah. So, between the three sigma boundaries, 99.7. That means 0.3% is both above and below. I
cut it in
cut
half.
0.3 in half. That's how I got 0.15.
Okay.
Is that close?
I don't know, my calculator doesn't do it.
Okay, it's close.
My calculator's done.
Okay, number 8. What do you think about number 8? It probably is. Let's work it now. How do we set it up? What am I doing to the random variable?
Subtracting 5. So our x random variable, it has a mean of 20. It has a sigma of 2. And then we're creating a new random variable y equals x minus 5. Okay, so we need the expected value of y.
What should we get here? Oh, we're adding. Sorry. I did it wrong.
Okay. The question is subtract. When I did the answer, I added. My bad. Okay. So how do we?
This is actually mini project 3.
Yeah. So when you're subtracting, you take the mean of your x minus that same constant. So 20 minus 5. We would expect the average of my new random variable to be 15. Okay. What's happening to the variance when you subtract the constant? Stays the same. So variance of y is equal to variance of x. Okay. So that means it's 2 squared, or 4, and that's standard deviation, square root of 4, or 2. Okay, B, new random variable is x1 plus x2. Anybody know what I mean when I'm saying that?
20 plus sigma plus sigma 1, the mean plus the first sigma.
Uh-huh. What do I mean by these subscripts? That's what I was asking Deanna. Yeah, it's like two random variables of x. But think of it as like one draw and then a second draw. Okay, this random variable has mean 20, standard deviation of 2. This also has mean 20, standard deviation of 2. Okay, usually these are independent. I don't think I wrote that down. Okay, so I want the mean and standard deviation of my new random variable. What happens when you're adding? Yeah, the means add. You should get 40. Andrew, what do the variance? What happens to the variances?
They add as well.
Yep. If independent. Be careful, I gave you standard deviations. I didn't give you variances. So you have to square those. We said standard deviation was 2, so I gotta square it.
that's 8. And then I can get the standard deviation and take the square root of the variance.
Okay, questions? Okay, I am gonna take question 9 off. We're just gonna go up to chapter 18.
Oh, you're awesome.
So I'm just shortening the test. I've already made it up, I'm just gonna tell you to X it out. So take question number 9 off. We'll pick it up when we get back. Okay, questions? Can I go back? And yes. Yep. Yeah, it's a short test. It'll be 8 questions. Yeah. Everybody okay?
It's not
Can you guys keep it down, please? Say again.
The normal is not one specific one page.
The normal is not. No, that's a Bernoulli is the broad name, and then depending upon if I want the, does that make sense?
Yeah.
And then depending if I want the first success, that's geometric. A certain number of successes in n trials, that's a binomial. They both fall under Bernoulli. Okay. Normal would be a quantitative number. So, anybody else? Okay, I'll see you on Thursday. I'm going to stick around if you have questions.
What?
There wasn't a number.
No, I'm not going to email it. I can just tell you, you can find it on my YouTube.
Oh, yeah.
I'll throw it down for you.
I was thinking that was an A and B.
Can I just go and email a link? And I've never emailed anybody from.
Because I have.
Okay.
I have.
I'll upload it to YouTube.